All right, so yesterday we left off and we were talking about why the model that we believed, or model of the atom, or what we believed the atom looked like, had to change as we discovered new things. Okay, so as science progressed, people were running experiments, and sometimes the results of those experiments could not be explained by the current model. Okay, so if you're doing science right, when that happens, then you have to adjust your model. Okay, and science is not always really good about doing things like that. Okay, a really good example would be when your parents, okay, were in like high school. They were probably taught that all life on Earth fit into two kingdoms, plants and animals. And that idea persisted for a very long time, even though we knew full well that some of the things we had put in those two groups didn't fit in those two groups. Right? For example, fungus was in the plant kingdom for a long, long time before finally somebody said, that's ridiculous. It's not a plant. What does a fungus not do that a plant does? Yeah, it carries out, it doesn't carry out photosynthesis. That's kind of a key piece of being a plant. But it grew out of the ground, so people just jammed it in there, okay? By the same kind of psychology of, well, I can't get this puzzle to work, that piece doesn't fit there, but if I pound it in hard enough, it'll work. Okay, like that was kind of the logic of the time. Okay, we can't do that. Good science doesn't work that way. If something doesn't fit the model, adjust the model. Okay, and the history of the atom is kind of filled with that. All right, so J.J. Thompson is the guy who discovered, okay, electrons, and as a result, he came up with the plum pudding model, okay, saying that, yes, I'm still going to keep Dalton's solid sphere, but there's these negative, or there's these electrical particles that are loosely embedded on the surface, and they can fall off in a reaction, and that's what causes electric currents. Okay, at the time, it was a logical, okay, conclusion. All right, once the electron was discovered, there was this parade of discovering new particles. Okay, so a bunch of experiments kind of came along, and it was discovered that, well, if there's a negative particle, then there has to be a positive particle, because otherwise the atom would be negatively charged. Now, J.J. Thompson's explanation for that was, well, the central sphere is positively charged, and all the little negative charges are on there, okay? But that doesn't really work very well, because when positives and negatives would actually touch each other, other things would happen. So it's not really, it didn't really fit. So they came up with, well, then there must be positively charged particles, and there must be maybe neutral particles to account for all the extra mass that couldn't be accounted for in an atom when reactions went on. There was a lot of really theoretical stuff that went on kind of in the early to mid 1900s, trying to figure out what exactly the atom looked like. Okay, all right. So we had people like, Chadwick and things like that who came along and discovered these other particles. All right, so 1932, James Chadwick discovered that protons were not the only large particle in the atom. Okay, he found that the mass of many elements was too large to be accounted for by only protons and electrons, because we knew electrons were practically massless. Okay, they're not, but they're so small. Okay. So he said, well, then there must be another particle, but it can't be charged, obviously, because then that would throw off all the charge balancing stuff. So there's this big neutral particle, and it's the same size, same mass as a proton, but it doesn't have a charge. We'll call it a neutron. Okay, so neutron carries no charge, okay, in there. Now, at that point, there's a whole bunch of different ideas about what the atom looks like. There's like modifications of plum pudding that have everything embedded in it, positive, negative, neutral. Okay, there's planetary models. There's all kinds of weird things, but nobody knows for sure what it looks like, because no one can see it, and there's not really any experiment that had been designed to prove what it looked like. Okay, there was a large group of people, however, who believed that the atom had a central dense nucleus. Okay, where like the positive charges would be, okay, and the neutrons, and then the electrons would be surrounding it in some manner that they didn't know, because obviously they couldn't tell what they looked like or how they were moving. Okay, so a guy came along, okay, and he said, I've got to design an experiment that can find out whether there is a nucleus or whether atoms are much bigger or smaller than people think. Okay, so a guy named Ernest Rutherford came along, and he said atoms couldn't have all those particles floating around randomly. Okay, it just wouldn't work. All right, the plum pudding model, solid sphere models, they didn't account for things. So he designed an experiment where he took a sheet, like a thin foil of gold. All right, so imagine what tin foil looks like, but he had a foil that was made out of gold, so it would have been really expensive. Okay, but he had this thin foil, really, really thin. Okay, and he shot essentially like X-rays or alpha particles at it. Okay, now his idea was that if atoms are big, when the alpha particles hit the foil, they'll bounce. He thought the atoms were really, really small. So he thought the alpha particles would go right through the foil, okay? And that none of them would bounce back, okay? So that was his idea, right? That all this stuff is just going to go through. And people laughed at him because they're like, you're shooting particles at something solid. What do you really think is going to happen? You think they're going to go through? That's ridiculous. They're going to bounce back. Everyone thought he was going to be proven wrong, okay? So he said, here's my model of the atom. There's a dense nucleus, and then the electrons are going around. Maybe they're all in concentric circles, okay, that are just offset slightly so that they don't run into each other, okay, something like that. So here's his experiment. He's got his source of the alpha particles right here. He's got his thin piece of gold foil, and wrapped around that, he has essentially photographic film. Okay, now you guys are of the generation where you probably never used a camera that had film in it, but there used to be film inside cameras. And when you opened the shutter, the film would be exposed to the light and the image would form on the film. Okay, so how film works is when light hits it, it changes. Okay, it's called exposure, right? And essentially it just gets bright instead of dark. Right? So he had this stuff around, and anywhere where an alpha particle would hit, there would be a white dot on the film. So his idea was that all the dots were going to be behind the film, okay, or behind the thin gold foil here. So he thought, this is where all the particles are going to go, is right there. I'm just going to get this big bright spot behind the foil because atoms are really, really small. In the end, this is what happens. He got bright spots in a lot of places. Yes, he still got most of them behind the foil, which proves that atoms are really small and have a dense nucleus, okay, but the nucleus was bigger than he thought. Okay, which means that protons and neutrons were bigger than he thought as well. Okay, so he got a few of the alpha particles to bounce off or be deflected to other places. So essentially, what happened was some of the alpha particles went right through. They didn't encounter any gold atoms, okay, or at least any nuclei of gold atoms. Right? So a lot of them did that, but some would hit the nucleus of a gold atom and be deflected. Right? Those would be the ones that would hit like over here or over here, not straight behind. Okay? So when he saw that, he was shocked, okay? Because his idea was that the atom was made of so much empty space that these alpha particles, which are really small, would just go right through. Okay? So to see them bounce back, okay, was shocking. He said it was like firing a 15-inch shell, so like an artillery shell, at a piece of tissue paper and have it bounce back. That's a little dramatic, but that's what he said. Okay? So his experiment proved the existence of the nucleus, and thus the nuclear model of the atom. Okay? If there wasn't a nucleus, okay, then all of the particles, okay, if it was like solid sphere or plum pudding, all the particles would have just bounced back. Okay? But a lot of them got through, which proves, yes, there's a central dense nucleus, it's small, and the electrons surround it. Okay? So that was the kind of an important experiment to prove the nuclear model and then lead to all kinds of nuclear science. Okay? Knowing that the atom has a nucleus means, okay, now we can start doing things like nuclear fission, nuclear fusion, explaining why they happen, okay, and things like that. So Rutherford, other than Dalton, probably the most important guy you need to remember. Okay? Dalton came up with the atomic theory, and Rutherford proved the existence of the nucleus. Okay, with his gold foil experiment. Okay, so once the existence of the nucleus was proven, then all the argument was about, all right, what are the electrons doing? Right? We can't design an experiment like this to find out where the electrons are. Electrons are incredibly small. They move incredibly fast, and we now know they move up and down as well as sideways. Their orbits aren't circular. Okay? They have all kinds of weird shapes, and in fact, we don't call them orbits. We say that the area where an electron can be found is an orbital. Okay? And it's a three-dimensional volume in which the electron has a high probability of existing. Okay? We can never pinpoint exactly where an electron is in an atom because it's always moving and it's incredibly small. Okay? But we know where it has a high likelihood of being. Okay? So it's like an exercise in probability. All right, so first experiments to prove kind of what the electrons look like were by Niels Bohr. Okay? And he showed that electrons do have different amounts of energy. And based on their amount of energy, they could be close to the nucleus, that would be the lowest energy, okay? Or they could be further away from the nucleus, that would be the higher energy levels, okay? But he was convinced that they were in orbits and that they shared these circular orbital paths, okay? Just like the planets around the sun. He was thinking that that's probably how it worked. And realistically, if you were to take a picture of an atom, it might look something like this because you would freeze the electrons in one place. Okay, and based on their energy, some of them might be the same distance away, but obviously not in the same place. Okay, but what we discovered later on is that their energy levels can change and they actually move up and down a lot. So they're not in concentric circles, they're in all these different places, okay, within the three-dimensional space surrounding the nucleus. All right, so Niels Bohr, important, okay? We still use the Bohr model to explain like bonding and how compounds work because it's simple, okay? And for all intents and purposes, a freeze frame of an atom, okay? But what's more accurate is what we call the electron cloud or quantum mechanical model, which says that electrons surround the nucleus in this cloud, okay? More electrons are close, okay, because that's the lower energy level, less electrons would be further away, okay? But all of these orbitals have weird shapes, and the more electrons an atom has, the more weirdly shaped orbitals it will have, okay, or that will be filled with electrons. Okay, so this is de Broglie's model, okay? So de Broglie is the one who came up with what we currently accept as the true model of the atom, okay? The electron cloud or quantum mechanical model. Okay, his experiments that proved this had to do with fluorescence. Okay, so if you have anything that like glows in the dark, okay, without a power supply, like you put it out in the sun, and then when you put it in the dark, it glows for a little while. Okay, that's fluorescence. And what happens is, when the solar energy, when the sun strikes that material, the electrons gain energy, and they jump from one energy level to another. So they jump away from the nucleus to a higher energy level. We call that a quantum leap because they're leaping from one quantum to another. All right. If you then remove that source of energy, that is, you go into the dark, okay, those electrons now can't maintain those high energy levels. So they start dropping back down to the lower levels. And when they do that, they release the energy back. So they glow while they're releasing that energy. That's why they don't glow forever, and they glow until all that energy they absorb is gone.
So do glow sticks work like that too? Or is that chemical?
That's a chemical reaction. Yeah, it's not the same thing. All right, so everyone kind of understand how that works? Okay, so that was the proof that electrons exist in this type of a state rather than in these fixed orbits that they can't move around in. Okay. All right, this is also how photosynthesis works. Okay, when sunlight strikes chlorophyll, the electrons in the chlorophyll get excited, they move away from the nucleus, and then as they fall back down, the energy they release is used to make sugar. Okay, that's the energy that powers photosynthesis. So that's how it's converting solar energy into chemical energy. It's actually using the falling electrons, okay, to gain the energy needed to make sugar. That is to split water, split carbon dioxide, and put them back together in a new arrangement. All right, questions on that? Okay. All right, so the structure of the atom as we currently understand it is that there is a positively charged, dense nucleus that contains the neutrons and protons. Okay, there is a large volume of space surrounding the nucleus in which the electrons can be found. Okay, so in fact, the atom is made up of a lot of empty space, and that has to do with a lot of the electromagnetic interactions between electrons and protons. Okay, because I mean, if you think about it simplistically, you think, okay, electrons are negative, the nucleus is positive. Why don't the electrons just fall to the nucleus? Okay, they should just move towards each other because they're opposite and opposites attract. Okay, but the fact of the matter is that when they're moving, okay, they stay a certain distance away. Okay, and so there's this electromagnetic kind of strong force in there that keeps them from crashing into one another. All right, one of the things you're going to be required to do for me is to essentially draw a picture of an atom. So if I say, here's an element, draw me a picture of what its atom would look like. All right, so for that, you need your periodic table. All right, so can everyone pull out the periodic table I gave them yesterday? So what I would expect to see when you draw a picture of an atom is that you would draw an electron cloud model, but you would also tell me how many protons, how many neutrons, and how many electrons are in that atom. Okay, so let's say we're doing this for, let's say for oxygen. Okay, so we'll say we're going to draw an atom of oxygen. Okay, so the atomic number for oxygen is 8. What does that number tell us? That is the number of protons. Okay, so things we need to remember that aren't in the notes package, so you might need to add these. Okay. Okay, and I am using this symbol as number, not hashtag of protons. Okay, it's number of protons. Okay? The whole meaning of that symbol has been horribly altered by your generation. Okay? It used to mean number. All right, so the atomic number is the number of protons. Okay, and then if I want to calculate the number of neutrons, anyone know how I do that? You subtract the atomic number from the atomic mass. Okay, so you go atomic mass minus the atomic number. All right, in a normal atom, how do I know the number of electrons? It's the same as the protons, right? Okay. Okay, that's in a normal atom. If the atom has undergone some kind of chemical reaction and lost an electron or lost 2 electrons, then it's an ion. Okay, now remember, in a reaction, you can only lose electrons. Okay, so atoms can gain or lose electrons. Why can't they gain or lose protons? Right, then they're either splitting the atom or they're fusing an atom. Okay, in either way, if you gain a proton, you've changed the nucleus. Okay, that's some sort of nuclear reaction, kaboom. Okay, and that's not good. All right, so you cannot change the nucleus in a chemical reaction. You can change the nucleus in a nuclear reaction, but not in a chemical reaction. All right. Okay, so if I want to draw, we were saying we were going to draw a picture of oxygen here then, okay, then this is what we would do. All right, I would put in that oxygen has 8 protons. All right, so I got my 8 protons, and I would probably like put a legend beside it, like, so no one was confused. All right, how many neutrons does oxygen have? 8, okay, because its atomic mass is 16, okay, and its atomic number is 8. 16 minus 8 is 8. All right, now its true mass is like 15.9994, but you can't have a partial neutron, okay? So never write in that something has like 4.27 neutrons. It doesn't, okay? You just round to the nearest whole number, okay? So we would have 8 neutrons. All right, and then I would write that this is a neutron. Okay, for the electrons, how many of them are there? There are 8. Okay, so this is what I would do since we're drawing the electron cloud. Cloud. I would just write that that's a cloud and that those are the electrons, okay? Okay, so I would look at that and go, okay, they know it's de Broglie's electron cloud model, okay? And they got all the particles in the right places, and they got the numbers of all the particles right. It'd be a 5-mark question. Okay, so 1 mark for the right model, 1 mark for putting protons and neutrons in the nucleus and electrons around the outside, okay, and 1 mark each for the right number of protons, neutrons, and electrons. Okay. I cannot remember the last time I did not ask that on a unit exam. Hint, hint. Good question. On your unit exam, can you use your periodic table? The answer is yes, provided you don't write too much on it. Okay, what I do is prior to the unit exam, I come around and I just look at your periodic table. Okay, if you've written essentially the class notes on it, I will give you a new one. Okay, but if it doesn't have too much written on it, okay, like basically there'll be a few times throughout the unit where I'll say, write this on your periodic table. Okay, the only thing then that should be on your periodic table come exam time is the stuff I've told you to add to it. Okay, which will basically be the prefixes for naming. Other than that, there shouldn't be anything to add to it. All right, so if you've written all kinds of rules, you know, about here's how I name this compound, here's how I name this one, here's all, no, then I'll have to give you a fresh one. Okay. Okay, so things to remember here, guys. All atoms of all elements are made of the same things. Okay, all atoms, all matter is made of protons, neutrons, and electrons. Okay, now in physics 30, you'll learn what protons, neutrons, and electrons are made out of, but for right now, we're just going to stop with, okay, they're made out of protons, neutrons, and electrons. If everything's made out of the same thing, how can anything be different? Right, well, we already talked about that. Okay, the way that different elements are different is because they have different numbers of those subatomic particles. Okay, it's the number of protons in the nucleus that determines the physical and chemical properties of that material. Okay, so it's these differing numbers of subatomic particles, protons in particular, that determine or influence the properties of each element. All right, now just to give you some idea, remember I said that the orbitals can be strangely shaped. Okay, this is more of the quantum mechanical model. Okay, there would be the nucleus here would be the purple thing, right? And then there are different orbitals. Okay, so there's the 1s orbital. Okay, so that would be here. This would be the 2s orbital, so you'd find some electrons in there. And then you can't have electrons getting too close to each other because they repel each other. So you start getting all these weirdly shaped areas where you could have a high probability of finding an electron. Okay, it gets really, really funky looking. Okay, when you start getting to bigger and bigger atoms. And that's the first thing you'll learn about in Chem 20 AP. Okay, is orbitals and electron configurations. So each atom would have a different electron configuration. So one atom might have like a 1s, 2s, 3p. Okay, and then another one would have a 1s, 2s, 2p configuration. It all depends. Okay, like it'll make more sense when you get there. All right, so there's a few questions here. They're actually in your notes package as well, I believe, okay, or in the worksheet book. They might be in the worksheet book, okay? But there's a few questions here that I want you guys to answer, right? Complete sentences, detailed answers, because this is the kind of thing that could maybe show up on a quiz next week. Spoiler alert, it'll probably show up on a quiz next week, okay? So you can find these answers in your notes and kind of combine them with your own knowledge, okay? No, because they're in your either, I think they're in the worksheet booklet, right? Yeah, so they're in, that's the first thing in the worksheet booklet is these questions. So you don't need to write them down, you already have them, okay? Just write down your answers, okay? Okay, so I'll give you a little bit of time to work on those. We probably won't get a chance to go through them together, but we'll go over them on Tuesday, okay?